Hi, my name is Ellie Hecker, and this is my Lab 5 on Faraday's Law. So the purpose of this experiment was to look at Faraday's Law by observing the interaction when a bar magnet was dropped through a conductive tube of aluminum foil. By doing this, we learned how time-varying magnetic fields affect electric fields and induce currents. After completing the experiment, I calculated the experimental fall time of the magnet to be 1.22 seconds, and the computational model I created calculated a fall time of 1.13 seconds. Some of the main physics principles used in this lab were the Biot-Savart law for a magnetic dipole and a point charge, which the equations are shown here. Faraday's law, which states that a changing magnetic field can induce a current in the surrounding objects, and also Newton's second and third laws involving net forces and their directions. In order to complete this experiment, the following process was completed. First, I used the magnetometer app from Lab 3 to mark magnetic north for the bar magnet. Next, I positioned the aluminum foil tube vertically and held the magnet just above the top opening, set up my phone, and then began to record the entire tube length. I scrubbed the video to determine the time that the magnet entered and exited the tube in order to determine the magnet's falling time. I did this 5 times and then calculated the average falling time for the magnet. This table shows the time in seconds that it took for the magnet to fall through the vertical aluminum foil tube in each of the 5 trials. The left column represents the trial number, while the right column represents the falling time in seconds. At the end, I calculated the average of these times and came up with an average experimental fall time of 1.22 seconds. Next, I created a computational model to simulate the falling time for the magnet falling through the vertical aluminum tube. I took measurements of the length, width, and inner radius of the tube to use in my calculations, which are shown here. And then I used the function to calculate the magnetic field of a bar magnet, which we created in Lab 3, which is shown down here. In this part of my code, I created a function to define the magnetic flux of the bar magnet, which is shown here. And then in these steps, I wrote code to calculate the current of the ring and then define the magnetic field at each of the rings. This line of code adds the magnetic and gravitational force in order to define the net force on the magnet, and then this line of code below updates the velocity and the position of the magnets over time. So this is the result when my code was ran. The computational fall time of the magnet was calculated to be 1.127 seconds, which is slightly quicker than the experimental time which I had calculated. Over here you can see the model of the vertical aluminum foil with the bar magnet at the bottom of the tube, and then this shows a velocity versus time graph for the magnet, and then my print statements are down here, which shows the computational fall time of 1.127 seconds. These are my interpretations involving the computational model. The color of the magnet, whether it was blue or red, would show the direction of the current. My current was red, which you can see here, which showed that the magnet falling produced a clockwise current. If the magnet was flipped around, then the dynamics of the system would be reversed, which means that the change in flux would flip, and then the current would also flip. Next, the computational model calculates a quicker magnetic falling time than we had observed. The computational model is less accurate than the experimental model because it does not account for air or conductivity resistance. So in order to make the computational system more accurate, we would have to add in some sort of code that would account for this resistance. And then lastly, the shape of the velocity versus time graph plot tells us that the net force eventually goes to 0 as the gravitational and magnetic forces become equivalent. To conclude this lab, what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced to nearly 0, then the magnet would fall more slowly. Using Ohm's law, which is V equals IR, we know that if the resistivity decreases, then the induced current would increase and the magnetic force would also increase. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, then the magnet would fall more quickly, the fall time would decrease, and then the induced current would be reduced and the magnetic force would decrease. Thank you.